Well, thank you very much for the opportunity to showcase our technology, essentially named as the pressure-induced fabrication. So this is a physical process that using pressure compression to fabricate multifunctional nanomaterials that has not been possible for the current chemical approach. All right. I really appreciate all the students and postdocs has been working with me in the adventure to invent this technology, and they have been very helpful, and they are the real heroes in this case. And our technology has received Sandia internal LDRD or Lab Directed Research and Development Program, and also DOE Basic Energy Science Program to demonstrate the concept from the low TRL from 1 to 3. And we also received the Sandia National Lab Tech Maturation Program support to demonstrate the large scale maturations of the technology up to like 5 TRL level. All right. So current nanomaterial synthesis has been dominated by chemical approach. So they have essential problems. For example, they are conducted in the non-ambient processing condition. For example, all the reactions need to conducted at a higher temperature or sometimes higher pressure, and they really need a complex chemical reactors. And the whole process or reactors are very expensive, and they often come with the side reactions and results in byproducts that you need environmental concerns and purification process that could cause extra monies. And you also need highly trained workers and operators to run the reactions. So we have opportunity to develop something that conduct at ambient condition or mild condition that reduce dramatically production costs. So that you don't need heating or special device that used in the reaction processing. And the pressure-induced fabrication dramatically improve the final material structures and achieve enhanced functionality or performance. And because we use a physical process so that the technology minimize the environmental and safety concerns. We don't have solvents or byproducts you need to purify or separate. And because the physical processing, we can directly make the material and integrate it into devices immediately. And in comparison with the chemical approach, you really need to purify the products and then integrate into the final devices. And here is the concept of our technology. So the overall, we use a physical pressure or stress compression to overcome the particles or material interactions at the beginning. And then so that when we compress them, we squeeze the material to contact and then glue or coalesce together to form new material that completely different from the starting material. They produce new functionality and structures. The whole process, you can imagine that they mimic the embossing or imprinting process. Is very fast. And we demonstrate the fastest process can take like a few hundred nanoseconds. So that overall cost is dramatically reduced. And because of the fast and physical process, and the reproducibility is very high. And the overall process conducted at ambient condition or very mild conditions. So as I show the structures over here, I'm not sure if you can see the tracer here. So they are all different and not been possibly achieved by the chemical approach. And the technology impacts broad applications. As I mentioned, we can produce the functionality in different nanostructures that the current chemical industry couldn't make. And we can make nanosensors, for example, the pressure sensors and stress sensors, which later I will touch base on. And because of using the high pressure process, we can produce very high densified materials, increase the memories of the devices. And we can make modulators to change the laser wavelengths. And we can reduce the defects and increase the purities and increase the material functions. I will show some of the applications later. And these materials, some of them semiconductors, and showing photocatalytic properties that we have demonstrated use for the phototherapies and killing bacteria. So that you can see the benefit of the technology is the whole process is very simple. You apply the physical stress or pressure, and we can produce very fine and clean results or products without separation or purification process, and no byproducts. We can easily integrate into the current manufacturing process, like I said, embossing or imprinting. So without invent a new expensive specialized equipments. And overall, the technology has been demonstrated to produce all sorts of metals and semiconductor materials. And because of the physical process, so there's no environmental harmful residues or chemicals. And I mentioned that the applications covered a broad area from materials, semiconductors, and optical devices, and phototherapeutics. And here are the few examples that I'm gonna discuss and showcase with you. The first one is the fabrication of functional materials in different structures. We have demonstrated using a large pressure device to produce the nanoparticle dimers and trimers and short nanorods and longer nanowires and 3D interconnected photo structures and nanosheet structures. As you see, that these are the electron microscope images of these structures and cartoons showing exactly what they look like in the nanometer scale. And the figure C, you can see that we can directly integrate into the 1 centimeter devices without purification process. And over here, the stress and pressure sensor, you can see that once we put a semiconductor material, they emit different color under the pressure. So you can see that at a different pressure, they show different color until about 7 gigapascal, that the color almost diminished and disappeared. But when you release these structure, these emissions of color can recover from the high pressure. So essentially during the 0 ambient condition to the 7 gigapascal, these process can sense all these pressures, which is very significant. And the next example is so-called pressure-tuned gallium nitride laser wavelength. So in the daily life, if you need to tune gallium nitride laser wavelengths, you will need to produce different gallium nitride structures. But using our pressure-induced technology, we can start the same one single materials. But when you apply pressure, you tuning the structure, and then you tuning the band gap and emit different color. As you can see that the wavelength is changing along with applied pressure from ambient condition up to 7 gigapascal, and you achieve different colors of lasers using one single materials, but using our pressure induced process technology. And the last example I'd like to showcase with you is to develop the photoactive nanomaterials that we can use to kill the bacteria or harmful microbes like the COVID-19 coronavirus. So as the figure A showing that the UV with spectrum of the high pressure process of the starting material, silver nanoparticles. So you can see all the surface plasma band start from 518 or 520 nanometers, changing back and forth up to 550 under different pressure. Those surface plasma band could eventually produce very sensitive like heat locally in a nanometer scale, so that they can kill the locally the virus or microbes or things like that. So that these spectrum can be controlled depending on the pressure and the materials that we can control at visible wavelengths up to near infrared or infrared spectrums. As you know, that infrared can produce heat and locally, and they can kill all sorts of bacteria. And that's all the slide I shared with you. And thank you very much for your attention. I'll be very happy to answer any questions you have.
Yeah. Thank you, Hongyou. We have time for just a couple of questions.
I'll start. Thank you for that presentation. Certainly an area of research that's quite interesting. And as you've noted, there are already other ways that this is done now. And there's certainly key industries or applications. My question is, what do you believe is the beachhead market where this ought to be tried first, in terms of there are less roadblocks for a particularly industry partner to create some benefit or derive benefit from this new approach? And at the core of that is the question of, what is the time to market to prove this out from the conceptual perspective right now to an application or a product?
Well, I would like to answer your last question first. So I think we have demonstrated that from TRL level from 1 to 5, we demonstrate different applications and different materials. And as far as the market standpoint, I think it depends on the applications or interest. And as I mentioned, our technology impact broad areas from synthesis to different devices. And I think if one of the company really interested in, for example, in the gallium nitride semiconductor area, I think we can work together to produce a device, and in that case, will be small devices that we can produce to for the gallium nitride lasers and integrate it. So we will focus on the integration part. So that's going to be the device part. But if we consider the fabrication, and then we will need to focus on the reactors to build a large-scale compression device to produce these materials.
Got it.
I'll give, hi, this is Mike. Could you just go to slide 5, please? I want to build on a little bit on Beto's question. These are very different markets and applications, which Beto was getting at. They're all very large. And so I guess I just want to maybe push you a little bit harder to say, where will you start? Because I don't think you exactly answered Beto's question. I think that was the main question I also had is, okay, there are many companies out there potentially you could go partner with. Which one or one or two are the most likely to adopt the technology the quickest, just based on your knowledge today?
Very good point. Thank you, Mike. I think there will be 2 points. The first one is the material part, synthesis or fabrication. So we need partners to work together to develop the large device to produce a large amount of materials that ready for different applications. So that's the first point, that we need to focus on the high pressure device to produce large scale materials. The second part is application part. It depending on the application interest. For example, like I mentioned, if you're interested, the company interested in the develop the laser applications, that we could focus on integrate the small devices instead of large. Now it's a small. into the device to sense the pressures or increase the memory of the device. And we could also reduce the gallium nitride or other semiconductor defects, which is the killers in the current industry, that you have all the yellow luminescence. But now when you introduce our technology in the integration process, you could get rid of the defect yellow luminescence and focus on the green lights. I hope I answered your question. So 2 points. One, we should focus on the partner to produce the device to manufacture the materials. And the second is to make a small device and integrate it into application device.